liftoff of the Delta II rocket with the Mars Exploration Rover.
Hello, I'm Venkatraman Patnaik and I'm studying in grade 6 on a Cambridge board. I'm starting with a brief introduction about myself. I'm a citizen scientist from NASA. I've qualified in 5 Microsoft Technology Associate Examinations in Java, JavaScript, HTML, CSS, Python and database. I got inspired or interested in space flight after the Chandrayaan 2 mission. It happened in 2019 and I was really excited to see India land on the moon. Unfortunately, it failed, but instead of getting disheartened, I got excited more. What made it fail? How could it have been fixed? And what are the signal systems that did take place making the failure? So I started to explore more in space science and space technology, and as I progressed, I got more and more interested. I approached my parents, I talked about it, and they helped me take multiple courses and try to find mentors for me in helping exploration for my journey in spaceflight. It was a very experiencing and fun journey so far, and I got to learn a lot from this journey. One of the things I learned is human spaceflight, and that is what I'll be giving a talk on today. Process and with all the good fundamentals and academics that will be checked by interviewers, the astronauts get selected. But it turns out that 100 is narrowed down even more. Some of these, mostly half of these astronauts turn into a backup or a ground astronaut for the spaceflight mission. The rest half get selected for flying into space. Usually they don't fly 50 people into space, so this is narrowed down into 10 selected astronauts for one spaceflight mission program. This means that from 10,000 that were applied, it just narrowed down to only 10 people that will be flying to space. So we got 10 people over here. We can't just shoot them off. We need to train. This is the second step. Training. Training will come as a training program. For India, these first astronauts were trained at Russia. For future missions of Gaganyaan, these astronauts will be trained here in India, as India is planning to build a training center over here. So we learned that there could be thousands of astronauts. We can narrow it down to a few tens of people. Now we have trained them. Apart from the astronauts process, we also have to design the spacecraft. So these are the next steps, the requirement to design the spacecraft. Usually there's a concept either from a student program or a selected concept from a NASA or a ISRO program as they'll be selected. Out of those concepts, if there are, for example, 100 concepts sent, it will be narrowed down to about 10 for human design spacecraft, ECLS systems, the environmental control and life support systems, and further systems that will be required to make sure that the humans inside the spacecraft are alive and safe. Apart from that, these 10 concepts are narrowed down to 1. So of course be selected in various ways, either through another selection process, through the uniqueness in the design, or most probably voting in the crew systems of what they find feasible. So we narrowed down one design concept to select and make a spacecraft. So we have the astronauts, we have the concept for the spacecraft. Now it's time to build it. The next step is spacecraft engineering. This means that they will turn this model or this concept of a spacecraft into a mock-up or a model, which they will then use to further simplify and create the system's design. So this scale model is created, usually 1:10, 1:5 or 1:2 ratio of models. Now that we created a model, this is very likely to be used for crew training, which I'll explain later. We have a model, we can use it to train the crew. It's called a mock-up model system, and we can also use it to briefly check on systems usage and abilities. Now we can build the real thing, testing. Testing of a spacecraft is very important. Not testing the spacecraft would mean a failure. This would just come grinding down that a nut got loose or a wire got broke. If that would happen in space, it would be a real problem and risking the astronauts. That would mean that we would need to constantly test these spacecrafts and multiple test process. Firstly, we can do the vibration test. Can it survive the vibration? This is very likely to happen in the vibration of the launch of a spacecraft, because a breaking nut would happen through the vibrating oscillations on the launch of a rocket. We won't want that to happen in space, so we figured out our problem and it's our job to rectify it. That's the vibration test. If we pass the vibration test, now we come into the thermal test. Here we will just put into the extreme temperatures of space. By extreme I mean the most extreme it can go. The hottest of 155 degrees Celsius and the coldest of 258 degrees Celsius. And that means that in negative 258 degrees Celsius, these spacecrafts will endure all the cold temperature and thermal stress of the aluminium or the metal body that is located for making the spacecraft. And as we increase the temperature to 155 C, this would mean that they can literally go as far as melting or rusting, something that we completely don't want to do, because these spacecrafts will just die out of their shape and it won't be possible to carry out the human spacecraft mission. So yes, during the design it's very likely that they chose the right component, but making it out of the right paint and the right metal as well is very important. And that's how we can test that this material, the raw material as well as the finished material, can pass thermal testing. From thermal testing, now we come into vacuum testing. Remember, space is a vacuum, there's no air in it. You and I can breathe air right now on Earth, no problem. But in space, it's a really tough time to do so. Because in space, we will be operating in a vacuum environment, which means there's no air, no pressure at all. And in space, we will be using a pressurized environment of the spacecraft. So which means that in a vacuum condition, when there's no pressure, we have to make sure that the air inside the spacecraft, the components and the humans inside the spacecraft are safe enough to operate and make sure that these spacecraft can operate in the harsh condition of vacuum in space. Last minute tests so that they can check on the components which we call subsystems in running the spacecraft. Assuming that this spacecraft has just survived the long, tedious process of a spacecraft working on these vacuum harsh conditions in space, we can now launch the spacecraft. Unmanned, that is, so there won't be any humans for now. This is what the first Gaganyaan will be doing. An unmanned mission, usually a robot or basically not having any manned components in it. This is another type of test. Everything. It will combine all tests and all hard work done and keeping it without humans. This is a demo mission. It will be carried out into multiple demo missions. ISRO currently plans to do 3 before launching a man into space. The first one is without any man or robot. They'll make sure that it can launch into space, it can stay in space for 1 whole week according to its intended mission, and then after that they would re-enter. Re-entry is a very tough process when you get down back into the atmosphere. Getting back into the atmosphere is not easy because space is a vacuum, so it has no pressure. But once you come into the atmosphere, the pressure suddenly increases. So which means that we can't design the spacecraft to be living under no pressure, right? That means we are currently coming down into the atmosphere with pressure all around the spacecraft, creating this heat, which we all think it's fire if you see on an imagery, but it turns out it's plasma. And as you know, on the states of matter, apart from solid, which is a solid component like ice, liquid, for example water, and then gas, which is vapor, plasma is just a completely different thing. It's the hottest thing that can exist, yet proven, and it's the 4th state of matter. So this is plasma all around the spacecraft, and it will be for the whole atmosphere until we come down into the normal pressure of 60 kilometers. Which means for 40 kilometers, we'll be around this plasma environment and gas pressurized environment on around the spacecraft. So this will be landing using a parachute and then will be coming down to the ocean. This is the first test, a very important test, and it will prove that the spacecraft is capable of doing a whole mission unmanned. Next, they'll do another mission like this, but place a robot. The robot is a female robot called Vyomitra, which will be carrying a humanoid type of system. So it will be a humanoid robot looking a lot like a human and will do basic operations that a human should do. They'll do 2 tests with Vyomitra. So this means that they have completed 3 orbital rocket tests. Assuming again that all of these tests have been passed by our spacecrafts, there needs to be a bit more of tests. These are called abort tests. The abort tests will test the abort systems on a spacecraft. So if you have seen a human spaceflight mission, you'll see a giant tower sitting atop. That is to save the astronaut's life. It will eject the astronaut capsule in case something goes wrong with the rocket. And so there are 2 types of abort tests. The pad abort test, which means the rocket was sitting on the launch pad, but it didn't turn out so good, so we decided to abort it on a ballistic trajectory to land back with the parachutes. Or else, there can be a case that the rocket was launched and then something went wrong. The rocket is about to blast, so we'll send the abort capsule before the abort window into a ballistic trajectory that will help it land back in the ocean. The second test, called the in-flight abort test, is a quite important test and will prove that this abort system can work on the ground as well as in the air before the abort window cuts off at T+2 minutes or 2 minutes after launch. That was long to just test, build and figure out a spacecraft. And we have finally made a successfully proven crew capsule. We also need a certified rocket for that. There's a certification process called a human man-rated vehicle. For this Gaganyaan process mission, we will be using GSLV Mark III, also known as LVM-3. It is a heavy lift vehicle and it can take things to geostationary orbit. It can take satellites there, but for now we'll be taking these missions to LEO, carrying the high power and capabilities required for a human spacecraft mission. The GSLV goes through multiple tests like the spacecraft, and those are long and tedious too. I won't go into that because those tests are actually the same pretty much as the crew capsule tests. Training the astronauts alongside that. So for astronaut training, there's a 1:2 ratio scale or 1:5 ratio scale made so that an astronaut can get into the spacecraft and train inside a mock-up. And usually these mock-ups can be half scale or full scale mock-ups, and astronauts get into that mock-up. They will train basics so that the buttons, the switches, and then the mission control requirements inside the spacecraft or the basic requirements for astronauts to operate can be trained there. Of course, they won't do vacuum training, zero-G training, etc. etc. But they will only train for normal missions. Next, if they complete that training, they will get into the next training system, the zero-G training. So the astronaut usually is out of the 50 or 100 selected astronauts, they all are usually zero-G trained, so they can survive zero-G environment and they know how to react in case there is a zero-G environment in their area. Now, this will completely take another round of training in a zero-G capsule, usually inside the water, that's the neutral buoyancy training, or they'll do this type of training in the air using a plane. So what usually happens is an airplane could take off and it could stay under normal G-force. Then they would dive and turn their engines off. There's no external force other than gravity. Gravity is pulling them down and there's no other force by the airplane that will keep them on their G-force. That's how we can stand here. Gravity is pushing us down, but we have our own force generated by our legs and limbs that can help us stay straight and make sure that there's no zero-G environment. But if we cut off the engines, there's no external force and they can now start flying in a zero-G environment. That is how they get an approximate idea of how zero gravity works, and that is how they'll learn to balance in a zero-G environment. Not only that, they'll now get into the water training. Basically, there will be their spacesuits. The EVA training will happen as they'll dive inside the water and they can hold their components and start to train how to bolt and bolt or fix a component that they want to fix. This is the usual category and requirements that are required to be any type of astronauts. After mock-up training, zero-G training on air and water, they'll start to do one last type of training. This is called basically health training. Crew balancing and health training is very important because as they'll be in space, doesn't matter for 1 week or for 6 months. They will be there in space losing their bone capacity and their calcium in their bones, which means that their bones will start to decay. Some have skin problems and skin effects, and there are multiple problems that can happen in space, and usually it will take at least 24 to 48 hours to come back. That is why every crew is a trained medical professional, at least in first aid, so that their crew and themselves are just stable in their stability and health. This is so that they can at least balance the first 24 to 48 hours before landing back onto the earth. These are the 4 major types of training any astronaut going to space has to qualify and endure. Once they do this, they are officially trained, a fully trained astronaut personnel. 15 days to 1 month before the space flight, put in quarantine so that they are stable, their health is stable, and that they won't spread any type of virus or any bacteria or disease that might affect population in space. Because there can be a virus on Earth. We have hospitals here to treat them. But there's no hospital in space. So if you have a disease at the last moment especially, it will be a really big loss for the spaceflight mission. This is how the crew trains and the spacecraft can fully certify into making sure that they can go to space. This is just post-mission, and it is very, very important to qualify all of this mission.